Okay, so we have spent a few weeks talking about the atmosphere, the components of the atmosphere, the layers of the atmosphere going from troposphere to exosphere. Then we looked at energy in the atmosphere, how energy travels from the sun through the electromagnetic spectrum, hits Earth, warms Earth in different ways depending on your location, how that cycles air, how moving air creates global winds that appear to curve by the Coriolis effect. And so before we jump into the weather that's created from this, there's one more thing we need to talk about, and that is water in the atmosphere. The water cycle dramatically impacts our weather. So many of you guys have heard about the water cycle before, have spent some time learning about the water cycle, maybe in elementary school, but just to make sure we're all on the same page, the water cycle is how water goes from Earth's surface up into the atmosphere through the process of evaporation or transpiration, if it's coming from plants, condenses into clouds, precipitates through snow or rain back onto Earth's surface. Some of it runs off into water bodies. Some of it infiltrates into the ground and feeds our plants and comes back up into the atmosphere again through the process of transpiration through plants or evaporation from the big bodies of water. Our atmosphere is dramatically affected by how much water vapor is in the air. It will determine what clouds we get, what kind of precipitation we get, if any, and the kind of weather that follows. Water is constantly being recycled from the liquid or solid state up into the gaseous state, back down into liquid or solid state as it reaches Earth again, depending on how it falls. So the water we have on planet Earth is the same water that was around when the dinosaurs were roaming Earth, which is a little disturbing because you might be drinking water that the dinosaurs peed in. Sorry. But it's constantly moving through Earth up into the atmosphere and back down. And that cycle is vital for all of the weather that we're going to be discussing. So let's take a moment and draw the water cycle. Don't freak out. It's going to be okay. Take some mountains and draw those mountains on your paper, nice and big. Then add in a little river coming down the mountain and flowing into a large body of water. It could be a lake like you see here. Eventually, it will flow into the ocean. And along these mountains, draw some trees. They can all look like Christmas trees or little triangles with stumps on them. It's okay. Okay, now let's draw where water is moving. Add in your arrows. Water evaporates from the ocean, from lakes, from streams, from liquid state, evaporating into a gaseous state, into our atmosphere. As it cools, it will condense into a cloud. Once that cloud becomes so dense, it rains down, it precipitates down. That water becomes too heavy for the cloud to keep it suspended. And if it's really cold, it will stay as snow or little ice crystals. If it's warm enough, it will come down as rain. So either way, it's precipitating back down onto Earth. So draw your little clouds, draw your precipitation, make sure you label it. Part of that precipitation is it's going to run over Earth's surface. We call that runoff, down little streams and valleys and things like that into lakes and oceans. And some of it is going to infiltrate into the ground, and we call that groundwater. So infiltration into the groundwater. That groundwater feeds all of our grasses and trees and other plants. So now water has gone from the atmosphere down to Earth and into Earth, and it's going to go back up into the atmosphere either through evaporation from ocean, lakes, and streams, or through transpiration, plant sweat. You guys learned about that last year. From all the plants on Earth's surface. So it feeds the plants, and any extra water they sweat out back up into the atmosphere, which will eventually condense into clouds, precipitate back down, so on and so forth, until we get this whole cycle. Oops, sorry, I moved your picture. Take a moment and watch the Study GMs video. You can pause this. Watch the Study GMs video. It's also under cool links on my website if you have a hard time clicking it from here. And it's just a quick review on the water cycle and how that works. Okay, water is in 4 different types in the atmosphere. So we see water as humidity. We experience it in condensation, in clouds, and precipitation. So these are our 4 big ideas for how water is in the atmosphere. Let's take a look first at humidity. Humidity is the amount of water vapor in the air. But what's tricky about humidity is the amount of water vapor that air can hold changes depending on how warm those air molecules are. So if you look at this graph, here's my amount of water vapor measured in grams per cubic meter, and here's my atmospheric temperature. So what I notice is warm air, remember this is in Celsius, so 30 degrees Celsius is actually really warm. Warm air holds a lot more water vapor, 50 grams per cubic meter, compared to cold air. So warm air holds a lot more water vapor than cold air. So how we actually measure humidity in the atmosphere, we don't take a direct measurement of the water vapor in the air. We measure the water vapor in the air compared to how much it actually could hold at any given temperature. Okay, so let's say it's 20 degrees Celsius. 20 degrees Celsius can hold a maximum amount of water vapor of 15 grams per cubic meter. So if I measure the air and I find that we have 10 grams per cubic meter, 10 grams out of a maximum of 15 grams is 66%. 10 divided by 15 is 2/3 or 66%. So that's actually called relative humidity. So relative humidity is the amount of water vapor in the air compared to the maximum amount that it can hold. So you look at your atmospheric temperature. We said 20 degrees Celsius. Maximum at saturation, the most it can hold, is 15 grams per cubic meter. If I measure my atmosphere and the water vapor in the atmosphere, the actual measurement, let's say, is 10 grams per cubic meter. That means 10 divided by 15 is 0.667 times 100 is 66.666 continuing percent. So 66 or 67% relative humidity. It's 67% of the maximum that it could be. Okay? And the tool that we use to do this is called a psychrometer. A psychrometer has 2 thermometers in it. One of them is a dry thermometer, what we normally use to measure temperature. Nothing new or fancy. The second thermometer is called a wet bulb thermometer. What you do is you take a little piece of cotton, almost like a tiny little sock, and you dip it in water and put it over the end of one of the thermometers, and that becomes a wet bulb thermometer. So a dry thermometer and a wet bulb thermometer, and we can see them side by side right here. And this handle actually spins around. So you go outside and you fling it around over and over and over for a minute or so. And what it's doing is it's recording the actual temperature of the atmosphere and the temperature of the atmosphere as water is evaporating. And that will indicate how much water vapor is in the air. So we have the temperature, the actual temperature of the atmosphere from the dry bulb, and then the wet bulb will have water evaporating as we spin it around in the air. It's drying as the water leaves the little sock that we put on there. And that will tell us, when we put it up against a fancy pants chart that meteorologists made for us, that will tell us the relative humidity in the air. So let's look at this psychrometer a little bit more closely. So here's my handle. Here's my wet bulb thermometer. There's the little sock on the end. Here's my dry thermometer. And when I go and spin this around the air like a crazy person, water is going to evaporate. This is going to start to dry off. Water is going to evaporate off of that thermometer. And as it does, it will measure a lower air temperature. So you can see my dry bulb thermometer measured my air temperature to here. My wet bulb thermometer says it's a little bit colder because it's evaporating. Same thing when you get out of the pool or get out of the lake, and even on a warm summer day as you're drying off without a towel, if the wind is drying you off, you feel chilly because water is evaporating off of your skin. So it makes you feel colder. So it's measuring the difference in that temperature from the wet bulb to the dry bulb. Okay? And what we do is we compare that to a chart. And we say, okay, if my dry bulb reading says it's 20 degrees outside, 20 degrees Celsius, and my wet bulb said it was 4 degrees cooler than that, so this is the difference between my wet and dry, then the humidity, the relative humidity is 66%. That means it's 66% of maximum saturation, the most water that it can hold. So the result of this is that 66% humidity on a warm day feels very different than 66% humidity on a cold day, because warm air holds more water vapor than cold air. So if you go outside in the summertime and the humidity is up in the 80s or 90%, that means 90% of the maximum amount of water vapor that warm air can hold is there. So it feels really sticky and hot and sweaty and uncomfortable and gross. Because 90% of a lot on a warm summer day is much more than 90% of very little on a cold winter day. Cold air holds much less water vapor. So 90% humidity in the winter doesn't feel like much. You can't tell. It doesn't feel sticky because 90% of very little water vapor is still very little, versus 90% of a lot of water vapor that warm air can hold in the summertime is a lot of water vapor, and it feels very sticky and sweaty and gross. So humidity is relative, and what we mean by that is it depends on the temperature of the air when we're looking at humidity. Warm air holds more water vapor than cold air. If you haven't noticed, I've said that like 8 times. So that's our big take-home message. Warm air holds more water vapor than cold air. Okay, number 2. The second way that water is in our atmosphere is in the process of condensation. So we learned about condensation back in first quarter when we were talking about states of matter, how things go from a solid to a liquid to a gas to a plasma and back. When we have a gas, its molecules are moving very quickly because it has a lot of heat energy. When those molecules slow down because they get colder, they slow enough through the process of condensation to become a liquid. So when we're talking about water, that means they're going from a water vapor, so a gas in our atmosphere, odorless, colorless, moving very quickly, to a liquid water. You experience this all the time in the summer when you have a nice glass of cold iced tea or lemonade or soda, and you go outside on a hot summer day and your glass starts to sweat. Well, we know glass can't really sweat. It's not liquid coming out of my glass. It's gas in the atmosphere, the hot air hitting the side of my cold glass, slows those gas molecules enough to condense them, to slow them down, more tightly pack them into a liquid. The same thing happens in our atmosphere. When warm air cools enough, it becomes condensed, it becomes liquid. And meteorologists can measure the temperature at which this happens, and it's called dew point. And you would think it would be the same all the time, but it's not. Dew point is the temperature at which gas will condense. So it just takes a difference between the hot air and the cold surface. So often the cold surface is Earth. So if I have a really hot summer day, and there's enough water vapor, because dew point is related to humidity, there's enough water vapor in the air that it will condense at over 76 degrees. That means that there is a lot of water vapor in the air. That means that it is really hot outside, and it's cooling at over 76 degrees. So my air is really hot and really saturated. So a really high dew point. That is miserable. It's official, according to the news. I pulled this picture off of a news website, a weather website. Officially categorized as miserable. If water condenses from a gas to a liquid at between 71 and 75 degrees Fahrenheit, it's still oppressive, as if that's some sort of upgrade. Then 66 to 70 is uncomfortable, 61 to 65 is getting sticky. Really, I'm not happy until it's way down here at pleasant or lower. So we want our atmosphere to be not so sticky and hot that it takes more than 55 degrees to get it to condense back into a liquid. Number 3, the third way that water is found in our atmosphere is formed in clouds. So clouds are water droplets or ice crystals, depending on how high they are in our atmosphere, that are suspended in the air on little pieces of dust. Without the dust, without little pieces of earth back up there, it would not happen. We would not have clouds. So they need that particle of dust. It could even be skin particles. That's a gross thought, but it's true. So they need little particles up in the air to suspend on. They can't just float on their own. And clouds form when the air is cooled and condensation occurs. And we get that in 4 ways. So when we have convection currents and warm air rises, and as it reaches higher altitudes, it spreads out and cools, and we get clouds. It happens because of topography. So warm air will rise up a mountain during mountain breezes and valley breezes. And as it goes up higher elevations, it will cool. It happens because of what we call a convergence of air. And we'll talk more about air masses and fronts later. But when we have big chunks of air that are pushing air from high to low pressure, and there's one trapped in between, we get a low pressure system, and then clouds form there. And then the last one is lifting along weather fronts. When I have a cold air mass and another cold air mass, trapping a warm air mass in between. This is a lot like your glass on a hot summer day. We have these cold air masses like your cold iced tea, and warm air touching those surfaces of those cold air masses, and it condenses along those cold air masses, and we get water droplets there. We get clouds to form on the dust particles. We have lots of different kinds and shapes of clouds. You can see just in these pictures, there's lots of different kinds and shapes of clouds. And we classify them by their shape, their form, and by how high they are in our atmosphere, their altitude. So let's take a look at the 3 main categories of clouds. Cumulus clouds, stratus clouds, cirrus clouds. These are our 3 main categories, and there's lots of different subcategories, but let's look at their features. Cumulus clouds are puffy white clouds. They have flat bottoms. I think of these like the Toy Story clouds. If you look at the wallpaper in Andy's room, Some of you are noticing. Some of you have no idea what I'm talking about, but it's okay. All the clouds that little kids draw, those are all cumulus clouds. Cum means lumped or clumped. So when you think of like piles of cotton balls that look like a cloud, those are cumulus clouds. Strata means layer. So stratus clouds are clouds that form in wide layers. They're not super thick, but they go for large distances. So they cover up a big portion of our sky, if not all of it from our perspective. And we have gray sky days, sort of drizzly, rainy, sad-looking days. Those are from stratus clouds. Cirrus clouds, I think Cirrus was one of the horses. I can't remember. It has something to do with mythology. But cirrus clouds look like horsetail whips. They're very feathery looking, very spread out. They're at very high elevations, so they are made of ice crystals rather than water droplets. They're not going to produce precipitation. We're not going to get rain from these kinds of clouds, but we are going to see cirrus clouds a lot. We'll talk more about cirrus clouds. So if we look at a whole bunch of different subcategories of clouds, you can see that there's not just cumulus, stratus, and cirrus clouds. We have things in between that sort of have features of both, like altostratus clouds. They're higher than regular stratus clouds, so they're a little bit more separated. We have cirrocumulus clouds. So they're at very high elevations like cirrus clouds, but they're clumpy like cumulus clouds. So they have some features of both. Stratocumulus clouds, they're low and wide like stratus clouds, but they're a little bit clumpy on top. So we have tons and tons of different clouds. This one is everybody's favorite because they talk about it in Up, the cumulonimbus cloud. Nimbo means dark, and so these are so dark because they're huge clouds. They're very, very tall. They have large columns, and that density of a cloud will block out a lot of light, so they appear to be very dark. It's not that anything within them is so dark, but that they're blocking out the light. And because they're so big and thick, they are going to bring a lot of water vapor with them, and it will become so dense that it will be hard to keep it suspended, and they drop a lot of precipitation. So these are storm clouds. They bring lots and lots of precipitation. If you look at a more realistic picture, here's a cumulonimbus cloud, really, really high into our atmosphere, dense, brings lots of storms, carries lots of energy. But you can see there's tons of different kinds of clouds. There's a really fun cloud called a lenticular cloud. It looks like a UFO. Look it up. It's really neat. There's other clouds that look like waves in the ocean, like surfing waves that make that curl shape. Those are really neat. There's tons and tons of different clouds. You can go pick your favorite kind of cloud. I'm not interested in you memorizing all these clouds. What I want you to see is there's a pattern, and that pattern means something. So if I look at all the clouds that have stratus as part of them, whether it's altostratus or nimbostratus or stratocumulus or just plain old stratus clouds, they're all bringing some sort of light precipitation. Anything with nimbo is going to be, nimbo again means dark, so these are thick, thick clouds. So they're going to bring lots of stormy weather. We're going to get big precipitation with nimbo being part of that cloud name. So there's a purpose and a method to the madness for naming clouds. They mean something, and they help us know about the weather, which brings us to our last way that we see water in the atmosphere. Precipitation. So there are 4 big categories of precipitation: rain, sleet, snow, and hail. And some of you may say, no, where's freezing rain? Freezing rain is the same thing as sleet. Sometimes we give these different names. So let's look at what's happening with these, and we'll start with rain. Rain's over here on the right-hand side. This is our most common form of precipitation because we receive enough warmth from the sun, from the electromagnetic spectrum, that our atmosphere tends to be warm much of the time. So as those ice crystals or water droplets fall from the clouds at high elevations, they fall through a warm band of our troposphere. And that warm band stays warm all the way down to Earth's surface. And so our ice crystal or water droplet falls and stays water. Sometimes it falls through a cold band. So all of our weather is happening in the troposphere, our lowest layer, but we can break that troposphere up into smaller bands of air. So here I have my cloud toward the top of my troposphere, and it's releasing an ice crystal or a water droplet, and it falls through a warm band of air, so it stays water. And then right before it hits the cold ground, it falls through a cold band of air, and so that water freezes and hits the ground. We call that sleet or freezing rain. So it happens just before it hits the surface, so it just barely stopped being water, and it hits the ground as a little ice droplet, and that's called freezing rain. Snow is over here on the far left-hand side. So this is when, as it falls from my cloud, it falls through only cold bands of atmosphere, and so it stays as that ice crystal as it hits the ground. Hail is the most interesting, I think. Hail is where it falls from our cloud and falls through alternating bands of warm and cold atmosphere. And the more bands it falls through that alternate like that, the larger the hailstone will be. So maybe it only falls through one warm band and one cold band. You get a tiny, maybe pea-sized hail, just tiny little hailstones. But if it falls through 5 or 10 of these alternating warm and cold bands, then we start getting huge hailstones that are the size of baseballs or softballs. I've even heard of like cantaloupe-sized hail. It's huge, and it does an enormous amount of damage because of how fast it's falling and accelerating toward Earth's surface. So all of these different kinds of precipitation will come because of the temperature of our atmosphere, which is the result of the indirect heating from sun on Earth's surface. We've talked about the layers of the atmosphere. All of our weather is happening in the troposphere. So now that we understand sort of those layers and the energy and how water is involved, now we're getting a little bit closer to being able to start talking about weathered patterns. Next, we're going to talk about air masses and fronts. You may have heard that as you've watched the news, and how those will start to formulate our weather patterns. Good job taking notes today. Put these in the rings of your binder at the back of the notes and handouts section, and you guys can be cleaned up and dismissed when your teacher says it's time. Have a great day.